So recall that when you have a distribution that the mean and the standard deviation will completely describe the distribution if it's a normal distribution. Um, so with that in mind, what we'd like to do is be able to find the mean and the standard deviation fairly easily of the sampling distribution for X bar. Sometimes that's also abbreviated like this, SDSM, sampling distribution of the sample mean, with sample size n. So first property of the sampling distribution is that if mu is the population mean and sigma is the population standard deviation, then we saw this in the examples that we did earlier. The mean of the X bar distribution, or the expected value of X bar, is the mean of the population, so the mean of the original data. And then if you look at the standard deviation of the X bar distribution, that's what they call standard error. It turns out that if you do that formula from the definition, you will always get the standard deviation of the population divided by square root of n. So this is a shortcut formula instead of doing this. Okay, so if you do that formula, you get the same thing. So you kind of take this as a theorem if you want to. Now notice as your sample size n increases, your standard deviation or standard error decreases because the denominator of the fraction gets bigger, so the ratio gets smaller. And then we have the following theorem. If your original data, your X distribution, is normal, then your X bar distribution, the sampling distribution for X bar, is also normal, and that's for all sample sizes. So if you start with a nice population, your sampling distribution will be nice and normal. Now, that's not always the case if your original distribution is not normal, not for all sample sizes. But if your sample size is big enough, it will be. So here's an example. Let's say we know our population mean is 100, and our population variance, sigma squared, is 16, and n is 225. We want to find the mean of the X bar distribution and the standard deviation. So, well, the mean of the X bar distribution is just the mean of the population, which is 100. And then here, sigma squared is equal to 16. So that means that sigma is going to be the square root of 16, which is 4. So that's our population standard deviation. And that means then that the standard deviation of the X bar distribution, which is sigma over square root of n, is going to be the 4 divided by root of the sample size, 225. And square root of 225 is 15. So this is 4 over 15, which is approximately 0.27. So now we know how to find mean and standard deviation of the sampling distribution very quickly if we know mean and standard deviation of the original distribution. But the real benefit for sampling distribution is even when you don't know the standard deviation of the population, you can estimate it. Right, because if we found the standard deviation of the X bar distribution and just multiply it by square root of n, we'll get the standard deviation of the population. So this is actually a special case, these properties of what's called the central limit theorem. So central limit theorem says that if you're given a random sample with n observations, so sample size n, from a population with a mean of mu and a standard deviation of sigma, then when n is big enough, and that generally means n greater than or equal 30, although that's not a hard and fast rule, but generally n greater than or equal 30, then the sampling distribution of X bar will be approximately normal with a mean of the original population and a standard deviation of sigma over square root of n. The larger sample size here, the better the normal approximation is going to be for your sampling distribution. So larger sample size here means that your standard deviation sigma X bar, right? Denominator gets bigger, sigma X bar gets smaller. That means that X bar estimates the population mean better So sample mean estimates population mean better.